Hi everybody, this is Dr. Nigro with another Physics Fundamentals screencast. This one is going to deal with drawing free body force diagrams for systems of objects versus individual objects. All right, so let's start with that word system. So systems mean you have two or more objects that move as one. All right. So when we talk about the forces acting upon a system, we have to look at the forces acting upon each object individually, compare those forces, see if any of them cancel out, and then draw the free body force diagram for the system. As we're doing those diagrams, we need to also include our equations. All right. So we're going to be looking at two types of forces here. We're going to look at external forces, right? The external forces are those that are coming from outside of the system. So those are going to be things like gravity, support force, applied force, tension. Then we're going to have a set of internal forces. And internal forces are going to be those due to the interaction of the objects with one another inside the system. So this is going to be Newton's third law for the most part. And these forces tend to cancel out so that when you get to the system free body diagram, they are not going to appear. All right. So when we put together these diagrams, all right, I always start by drawing the free body force diagram. Sorry, I don't want to write that out for each object within that system. All right, so if you have two objects, you're going to draw two. If you have three, you'll draw three. Oops, that's not two is next. All right, after I draw those free body diagrams, I'm going to write my FNet equations for each object. All right. If you have a particular system that's moving, all right, then I'm going to kind of think about these objects in terms of parallel to the motion and then perpendicular to the motion. And we'll see that when we do some examples. All right. Once I have all of that completed, I'm going to cross out any action-reaction pairs. All right, and we'll talk about that, how you can spot those. They most often are due to objects resting on top of one another or objects connected to one another through some sort of cable, rope, or string. All right, once I finish crossing out those pairs, I'm going to look and see what's left, and I'm going to draw my free body force diagram of the system and then write the FNet equation based on that diagram. Oops. All right, so drawing these free body diagrams can be exactly like what we did before. The difference is we're going to basically add two free body diagrams together. I kind of think of it as overlaying them. And if I have any of these action-reaction forces, they're going to cancel each other out. And then we'll draw the system. All right, so let's move down and try a couple of these. All right, so for the following problems, we're going to draw the free body force diagram and write the net force equation for each mass and the system as a whole. All right, as we do that, we're going to keep three things in mind. First, the sign of FNet for each mass and system must be the same. All right, and FNet needs to be the same sign as the direction of motion if there is one, and we'll talk about that too. All right, remember, internal forces cancel out when you look at the system as a whole, and this is going to be due to Newton's third law. So every action has an equal but opposite reaction. And then for our purposes, if an object is on wheels, we're going to assume no friction. All right, so let's look at our first system. All right, here we have two carts, and there is applied force being applied towards the left on cart B. All right, first thing to keep in mind, you can see that they have wheels. All right, so what that tells me is that there is no friction, all right, which is going to make our stuff a little bit easier. All right, so again, we start with our individual objects. So I'm going to start with A. All right, so I've got vertical forces acting on A. I've got its gravitational force, and then opposing that is the normal force. All right, there's no indication that A is moving vertically, so I'm going to go with those being equal and opposite. All right, now there's another force that's acting on A, but is acting in the horizontal direction, and that is the interaction with cart B. All right, so cart B pushes on cart A. All right, so we call this force of B on A. All right, so that is what our force diagram looks like for mass A. So let's write our F net. So we're going to start with the perpendicular F net, all right? And that's going to be our vertical forces in this case. So we're going to have the normal force and the gravitational force, all right? And we know that this is actually equal to 0 because those are equal but balanced, all right? But we could put in our signs. We have a positive sign for our normal force and a negative sign for our gravitational force. Because remember, our positive forces are to the right and up, and our negative forces are to the left and down. All right. We also need to write the F net for forces that are parallel to our motion. All right. And in this case, the only horizontal force is that force due to that interaction between B and A. All right. For this particular diagram, that force is going to be in the negative direction, which means F net is going to have to be negative here. All right. Which makes sense because it looks like based on our applied force, the motion has to be in this direction. All right, so that means the F net and the motion have the same sign, which is going to be negative. Okay, all right, let's try B. All right, so here's object B. All right, we're going to have very similar vertical forces, except they'll be for B. So the gravitational force on B counteracted by the normal force on B. These are equal and opposite. All right, horizontally, we have the force of A on B, so that is the reaction to our action. And countering that, we have, oops, it's a little wrong room, an applied force. All right, that's this force right here. Okay, so I don't know whether those are equal but opposite. I'm going to assume that they are not because the object is moving. All right, so let's write our F net equations. Okay, we'll start again with our perpendicular. All right, that's going to again be the normal force, but for B, plus the gravitational force for B. All right, and similar to before, that gravitational force is negative, the normal force is positive, and F net will be 0. We move down to our parallel forces. Here we have two. We have the applied force, and then we have the force of A on B. All right, and we know that our applied force is to the left, which makes it negative. The reaction force is to the right, which makes it positive. And because of motion, we know F net needs to be negative. All right, so we're going to move on to our system. All right, so I'll draw that one in red. So over here, I'm going to draw the system. All right, so I need to look at what's available. So I'm not going to have any forces vertically or horizontally here. Vertically, because they've all canceled out. So I'm only going to be looking at the horizontal forces. All right, and if I look, I've got this force due to the interaction of A and B, and then I've got this force due to the interaction of A and B. Those are internal forces. So those are going to cancel. So they're not going to be present in the overall system. All right, but I do have one force left, and that's the applied force. All right, so if I want to draw my net equation for the system, it's going to be equal to that applied force. All right, and since that applied force is to the left, we're going to get a negative sign for the net system. Okay, so again, the key here is drawing out our individual diagrams, canceling out any action-reaction forces that we have, and then seeing what remains. All right, let's try another one. This one is just two objects sitting on top of each other. All right, I'm going to call this top book A, and I'll call the bottom book B. All right, so again, we split it. So I'm going to have, let's do A. All right, so we've got gravity pulling down on A, and then we've got the reaction action force of B pushing up on A. All right, now we don't put the normal force in here because right now the reaction action force is standing in for that normal force, so we don't have to include that. All right, and that's it. So we're going to move on to B. All right, and in my diagram, I whited out the arrow. We're not going to consider an applied force for this example, so we're just going to leave it off. All right, so now I look at B. So B also has a gravitational force pulling down on it. All right, and it has a force pushing up. That's going to be my normal force. But in addition to my gravitational force, there's a second force that's pushing down on my book. All right, so I'm going to slide this over a little bit, all right, to give myself room to add in my force of A on B. Okay, so these are the three forces that we see acting on force or book B. All right, so we we write our FNet equations. Come here, buddy. All right, so FNet and everything for this particular figure and both of them is going to be up and down, so we don't need to designate parallel or perpendicular, but FNet here will be the force of B on A plus the gravitational force of A. All right, and then for book B, the FNet equation is going to be equal to the normal force plus the force of A on B plus the force of gravity on B. All right, for signs, anything pointing up is positive, anything pointing down is negative, and the book isn't moving, so I know that FNet has to be 0. The force of B on A is positive, and the force of gravity is negative. Again, FNet for B is also 0 because it's not moving. The normal force is positive. The action-reaction force is negative, and the force of gravity on B is also negative. All right, so I look to see if I have any internal forces, and I do. I have this internal force and this one. Those two are equal and opposite, so they're going to cancel each other out. So they're going to be gone, which means I'm going to have my two gravitational forces and then the normal force acting on this system. All right, so I go back and I draw my system. Wait. All right, so I'm going to have a normal force, and that normal force is equal and opposite to my gravitational force of A and B added together. All right, so these two are equal and opposite, which is what we would expect because the objects aren't moving. All right, so our F net is going to be equal to that normal force plus the force due to gravity on A plus the force due to gravity on B. All right, for our signs, we have a positive normal force, a negative gravitational force for A, and a negative gravitational force for B, and an F net equal to 0. Okay? All right, now let's move on to strings and pulleys. All right, our first example shown here has a special name. This is called an Atwood machine. An Atwood machine is one that we have two masses that are connected via a string over a pulley. All right, so instead of having action and reaction forces because they're touching each other, our action and reaction forces are going to be propagated through the string. So our tensional forces here are going to be equal and opposite. All right, but we'll look at that when we get there. All right, the first thing to look at is how are the masses compared to one another. So we can determine whether the masses are equal or not based on whether they're resting at the same height or different heights. So in this case, mass 2 is lower than mass 1. So that tells me that mass 1 is a lower mass than mass 2. All right? So that means the objects must have moved at some point, and in this case, they must have moved towards mass 2's position. So our motion is going to be to the right, and that is designated as a positive direction. So that means that F net should be positive when we're finished. All right? So let's start with our first mass. Oh, before we get to that, I should say the easiest way to look at objects that are connected via pulleys, because it gets a little confusing because they both appear to be in the same direction, is to take those masses and the string and just remove the pulley and lay them out on your bench in your mind, obviously. All right. And then look at each of them individually. All right. You're still going to have gravity and those things. They're just going to point in slightly different directions than you would think. All right. So let's start with mass. Whoops, that's a B. Oops. Let me do this again. Mass number 1. All right. So I know that I have gravity pulling down. All right. So once I lay it out flat, that gravitational value is over here. So this is the gravitational value for 1, and then opposing that, I have a tensional force. Now, I know that the object has moved up, all right, so that tells me that my tensional force is greater than my gravitational force, or gravity would have pulled it towards the ground instead. All right, so these are not equal and opposite. All right, so we're going to write our F net for this object. That's going to be force due to gravity plus that tensional force. All right, we know that F net's not 0. All right, we know, in fact, that it has to be positive because of the direction of motion. All right, FG is still negative because in our new drawing, it's still pointed left, and tensional force is positive because it's pointed right, and because we know that tensional force must be greater, it makes sense that F net is going to be positive. All right, we're going to repeat. This time we're going to look at mass 2. All right, gravity in this case points in the other direction, and we have a tensional force that points in this direction. All right, I need a little bit more room. Here. Hold on, let me try that again. You know what, let me slide this guy over. That'll help. All right, sorry. All right, so we've got mass 2. All right, so the tensional force, because it's an action-reaction pair, has to be the same value as the one we saw for mass number 1. So that's why I'm going to give myself room. But I know that the object is moving down, so it's moving towards gravity, which means my gravitational force for object 2 must be greater. That's why I had to give myself a little bit more room. All right, so when I write my F net equation here, I'm again going to have a tension force on 2 and a gravitational force on 2. All right, I know that the gravitational force, which is pointed right, is positive. The tension force is left, which is negative. And because of motion, F net must be positive. All right, and it makes sense because my gravitational force is greater than my tension force. So my positive value is greater than my negative. So my overall value will be positive. All right, now moving on to the system. The first thing I do is look for internal forces. I have 2. I have these tension forces, and they will be equal but opposite, which means that when I add everything together, they're going to cancel each other out. So we just get rid of those, and we look at what is left. All right, so here's my system. I'm going to have a gravitational force from mass 2 pulling in one direction, and a lesser gravitational force from 1 pulling in the other direction, which means my net force for the system is going to be equal to FG1 and FG2. All right, for my signs, I'm going to have a positive value for FG2, a negative value for FG1, and my overall system value will be positive. All right, so when you're working these problems, you need to really think about how do M1 and M2 interact. All right, so if M1 is less than M2 in terms of mass, then your net force will be positive if you draw it the way we have, with M1 on the left and M2 on the right. If M1 is greater than M2 in mass, then your net force will be negative. And in the case that the two are equal to each other, then there'll be no motion, so F net will be equal to 0. All right, last one. We call this a cart and hanger. All right, in this case, my cart does not have wheels. All right, so that means that we are going to have a little bit of friction here. All right, if your cart has wheels, no friction, it makes things a lot easier. All right, now in this case, the mass always pulls down. So it pulls the cart along the bench, which means the motion is always in the direction of the mass, and we call that the positive direction. All right, we're once again going to have two objects to deal with. We're going to have what's called our cart and then what's called our hanger. All right, so we're going to start with the cart, which is up on the bench. All right. Sorry about that. I'm in my classroom at school and I can't control that. All right, so let's continue with this. All right, so we're going to have our vertical forces. So we have our support force and then we have our gravitational force. All right, and then in addition, we're going to have a frictional force and we're going to have a greater tension force. All right. So we've got those forces working for us. Our equal and opposite forces are our vertical forces this time. So we're going to have a net force perpendicular to the motion, which is our vertical forces here, of a gravitational force and a normal force. All right, this is going to be, the net force will be 0, our gravitational force, will be negative, and our normal force will be positive. All right, we then look at our parallel forces. Those net forces are going to be equal to our frictional force and that force due to tension. All right. The motion is positive, so F net's going to need to be positive here. Our frictional force will be negative and our tension force will be positive. All right. So let's move on to our hanger. Now our hanger, we're going to treat like we did our Atwood machine. We're going to pull it up so it is in the same plane of motion as our cart. It just makes things visually a little easier. I think I didn't give myself enough room. That's okay. I'll figure it out. I'll put it up here. All right. If we do that, then our gravitational force will be pointing towards the right. All right. And then countering that at a lesser degree is going to be our tension force. Whoops. All right. So we only have one net F net equation to write here. All right, and that's going to be equal to that gravitational force plus that tension force. All right, for signs, we know because of motion, we're going to have a positive F net, and our gravitational force points to the right, so it's positive, and our tension force points to the left, so it's negative. All right, so when it comes to internal forces, we have two. It's our tension forces. These are equal but opposite. All right, so that when we add together our F net parallel from our cart, it's going to cancel with our F net for our mass number 2. All right, now we are not going to consider the perpendicular forces acting on mass 1 because they cancel each other out and they're irrelevant to the motion. All right, so now let's talk about the system. All right, so our system has two forces acting on it. It has, in one direction, the force due to gravity from object 2, and in the other, the force due to friction between the bottom of mass 1 and the bench. All right, now we know the object has moved towards the pulley, which means that we must have a greater amount of gravitational pull on mass 2 versus that friction. All right, for signs, we're going to have a positive gravitational pull and a negative frictional force. So when we write our F net equation for our system, it's going to be that gravitational force plus that frictional force. And when it comes to signs, we're going to have a positive value for the gravitational force, a negative value for friction, and we'll have a positive value for the system. Okay? Now, if we put wheels on that first mass, then the frictional part goes away and our system's F net is only due to the gravitational pull on mass number 2. Okay? All right, so that's just examples of several different types of systems. All right, these take practice, so just make sure you're practicing and let me know if there are any questions.